Oh no, it was
which
late
is
in
like
the.
all the time.
It was later in the game.
Yeah, but it was like when we were talking to Tim, and then
Yeah, when
you
Tim.
had mentioned the top side. I'm like, oh, that must be what it is because
Yeah,
the light.
top had
So that whole time there was a idiot light that I missed.
possibly.
Possibly, but more like I think it's when
Usually my eyes glue into the, oh, I broke the shell.
no,
Oh no.
I would have noticed it. I think
Yeah.
it popped up probably when we started trying to actually interact with the GUI.
Yeah.
Yeah. Usually any red on that screen is painfully obvious. We're talking about our graphical user interface up here, and we have dash lights that give us green is good, yellow is lost, and red is bad. I really want to suck that shell out of there.
Yeah, you could probably place it off to the side.
That thing is huge.
It's probably a Native American artifact, that thing.
There you go.
Bye, Shell.
Okay, you know what to do, Michael. Thank you.
Dibs. That goes in the bio box.
100%?
100%.
Roger. Thank you.
Oh wow, that current's strong.
Yeah, it's pushing that shell right back.
Hurry up, get it. Put it in the bio box. For me.
I don't think we're allowed to.
I do it for you.
Not how the science vessel works.
No? We don't share things?
We don't.
It's
We
like,
don't share information and
it's like
specimens?
picking up rocks in a national park, man. Need a permit for that shell.
Oh.
Walls are pretty steep.
Is
I'm gonna
Dr.
use,
Freeze still?
what's that, bud?
I was asking if the doctor's I have another question.
Okay.
Are you
I hope it's
able,
not- yeah,
in your experience, have you been able to, with the amount of samples you get to, like extrapolate like a structure of the of different meteors, like the atomic structures and molecular structures from small samples?
You mean like composition?
Yeah, I guess. I already asked that. I was just trying to get like I guess, I don't know.
Your interviewing skills.
Yeah, yeah.
He really wants to add that to the resume as well.
I'm trying. I like atomic structures.
Answer is yeah. Excuse me a second.
Well, I guess because before what I was asking is more like what type of elements, compositions, and stuff like that. That's what I was kind of going for. And in this sense, I'm like, can you, how many different combinations of structures do those elements come in?
Sure. So simple answer is many. There's basically your meteorites are rocks. They are never a single mineral. There's always a range of compositions, a range of different mineral types, a range of there can be a range of textures in them. Sorry, I'm giving you it's 3 a.m. my time, and just not built for.
No, we appreciate it.
I'm gonna come up and change my heading 90 degrees so we can see long ways into the trench there.
Roger.
So it's getting too deep to see with the main camera. We can see with one of our other cameras, but
The dust is it helping? Copy.
Here we go. Can you straighten up the brow camera for us? So this will be closer to the original footprint that we spotted when we came down.
That looks kind of cool.
Yeah, it looks pretty ominous.
Yeah. I'm bummed. This is like the first time I can't get all these cool Argus shots.
I'm going to keep digging. We're going to find Jimmy Hoffa there. Ooh, the current is ripping.
Yeah. Oh no, my shell.
That's full jam to the left there. Broadside into the wind.
Is it possible for us to get in, block it so it doesn't blow as much?
Sorry,
Or-
say again, Michael?
Yeah, then the dredge stuff that
Oh.
will come back and haunt us.
You're right. You're right. I forgot about the dredge. So the exhaust.
Stop it. Marlon, can you zoom out for a second for us?
Yep.
Thank you. That's good.
Second.
Make sure I had the manipulator in the right place there. Okay, you can zoom back in. That's good, thank you.
All right.
Resuming.
Okay. All right, very nice. A little different perspective. Getting back. Sorry, go ahead.
We may have to widen a little. We'll see how we go here. Maybe if I go like this, we'll. Yeah, go ahead.
I suspect you will have to widen. Looks like it's slumping on the left side.
It is.
It's kind of threatening to fall into the hole there.
Best to widen before it collapses, I think. Stand
All
by
right,
for
so to
widening.
answer.
Uh-oh. Where?
Oh no.
Sorry, Dr. Price, go ahead.
No, that's fine. I'm trying to I'm trying not to talk over y'all while you're doing important excavatory things. So to answer the question of structures and mineralogy and features in meteorites, it's a good question. It's an interesting question because, like I was saying before, these things very, very early in the formation of the solar system. They're some of the first steps toward creating planets, and so you get mineralogy of basically something that condensed out of the very early primordial materials of the solar system, and so you do get a range of minerals. You don't just get a single mineral in any one meteorite. It tends to be the sort of minerals that you get when you similar types of minerals that you get when you solidify a magma. You get a lot of high temperature igneous minerals like olivine and pyroxene, and in that way it's similar to some of the minerals that you see in basalts overall on basalts on Earth. The big difference is that big difference between meteorites and rocks that you see around you on Earth is that the asteroids where these things come from are missing two major influences that you see in rocks on Earth, and one is water, and the other is biology, is life. The rocks that you see in a meteorite are typically most of them have seen no water or almost no water for their entire lives, and they've been kept cold and dry in the vacuum of space since they were formed 4.5 billion years ago. There are some meteorites that have been wet. Use the term kind of loosely because probably none of them ever had liquid water flowing over the surface, but they would have something more like steam flowing through them. And those are the carbonaceous chondrites, things that came from large-ish, well, no, I take that back. They don't even have to be large, but their parent bodies, they're
be all right to turn the Norbit on? That's what we were trying to do back in the day. All right. Thanks.
Sorry, Dr. Freeze.
Okay, no worries. So, yeah, the major difference is basically asteroids have a range of different mineralogy types, but by and large, they've never been wet, or they've only barely been wet for a little while, and they've never had anything eating them, any life in them, and so what you get is, I mean, look at what you're looking at here on the screen. A lot of this is clays. It's obviously sitting down under 100 meters of seawater, and it's slowly getting altered. The original rock that made up the seafloor is getting turned into mostly clays. There are some meteorites with clays in them, but they're very much not the norm. But by norm, I mean making up the bulk of most of the meteorites you see are just dry, have been dry most of their lives, and are formed of these igneous materials. So that's kind of a rambling answer. I hope that makes sense. The basic. Okay, so there's analogs. There's minerals that we find on Earth that we also find in meteorites. But by and large, the picture you see is that those analogs are the high temperature igneous rocks on Earth. Not all of them, but most. There are most of the major differences. You know, when we get a sample in the laboratory, the technology available to us today, the analytical technology lets us take these things apart down to the atomic level, and we can measure mineral composition, mineral textures, elemental composition, what elements are present in all these different minerals, and isotopes, the different isotopes that are present in the different minerals. And there are differences there in isotopic composition of meteorites versus stuff on Earth. One of the most commonly used, one of the most commonly used isotopes is oxygen isotopes for classifying meteorites. Basically, the oxygen in your typical meteorite is coming from originally some liquid melt, whereas most of the oxygen on Earth is in the atmosphere, and so they behave differently, as in a chemical sense, and so you get a isotope signature in meteorites is very distinct, enough that you can classify meteorites by their oxygen isotope. Yeah, so there's differences, but you're not going. There's some I've been asked in the past. Do you see minerals in meteorites that you just don't see anywhere on Earth? The answer is no. for the most part. You know, there's a few really exotic things that are formed by powerful impacts, and so those belong in the exception to the rule category because there's always an exception. But by and large, the minerals you see in meteorites have very similar. They're also found in terrestrial rocks. The textures can be different. The isotopic signature can definitely be different. But you know, there's no unobtainium oxide in meteorites.
Oh, thank you. Very enlightening.
Yeah, I hope it is. I feel like I'm rambling here. It is. We are now at 4 o'clock in Houston, Texas. Good
yeah.
morning.
Nope, you're helping provide us with some entertainment, so it's good. So do we think that a lot of sediment has since pooled on top of the original site? I guess we still saw the excavation scar.
The original excavation scar, I would, remembering back, was probably about 6 inches deep at most.
Oh, okay.
But the original pit was less than that. It was like 3 or 4 inches, and I don't see any trace of the original pit. You all have a better view of this than I do, but we could see the scar. So we're talking somewhere between 4 to 6 inches.
Michael, did you see that with your excellent eyes? I think we saw no evidence of the actual initial depression, right?
No, I don't think so.
Yeah.
I mean, what we saw when we pulled up, that's what I saw earlier. There's evidence of the original excavation site. If we saw anything like that.
That was 6 inches deep, you said?
About. Well, let's see.
Dr. Freese, the original one?
That's about right. We were basically, yes, that's about right.
All right.
Should probably put on my glasses.
So how deep are we thinking on excavating?
Since we don't know how deep this meteorite is, deeper is better.
All right.
You know, if we can get tens of centimeters or even a meter down, I'm not going to tell you to stop digging. We're
right.
eventually going to run out of time or find a meteorite.
Just add it for 16 hours.
Is that your bet?
Yeah, but they have a wall.
Yeah.
An anti-collapse wall.
And there's pros and cons. They have a wall, but they also don't. This doesn't also have glass, so it's a lot easier.
That's right. No, I think you're right though, Dan. If you slope down the sides, yeah. If the sides slope down, I think.
Let's see if we can get the 5 and just kind of like.
At some point, we're going to want to put the magnet in there and see if anything sticks to it.
Yeah, when would you like to do that? Later on or sooner?
I think later on.
All right.
I think we're getting down into the ballpark.
All right.
Part of the problem is we don't know the size of the object that created this pit, but it's probably on the order of a few tens of centimeters.
Yeah.
Let me check it out.
We have a innocent bystander at the top of the screen. Crab just showed up.
Oh. Oh, look at that.
Whoa.
Yeah. You're not on SPL, Dan, by the way.
Oh, he's gonna get up all up in there.
Oh, he's like, I think I might just get up in there. He's eyeing it.
Shoo! Go on now, get.
I'm gonna
Oh,
Yep, there it is.
Oh.
No.
oh,
I'm gonna move the vehicle to the left just a little bit so our hose
Pretty
is
big
not
crab.
caving in the porch here.
It is approximately 10 centimeters.
yeah, I know. I was looking at that too.
Tim,
How can you tell that, Michael?
Oh, there we go. The
Yeah,
Norbit.
this is
Norbit
great
works.
eyesight.
Fish.
Just excellent vision.
This is without my glasses.
Yeah, there's a fish off to the right there behind the hose.
So a fish and a crab come to a hole.
Up.
Oh,
Just trying to get reprieve from the current.
Get out of there.
oh yeah.
Oh, this
Oh.
crab is fearless. Oh no.
Oh, you gotta suck it up and then move it.
I need to turn down for that.
Just gonna touch him. He should run
Oh,
away.
there we go.
Run away quickly.
Tim, do you need that Norbit on still?
That was, what are you trying to
yeah.
ask Tim?
Yeah.
A little bit more
he'll come
clear,
back.
so.
I gotta say the Argus view is my favorite. It's very interesting right now.
Right? Isn't it just like you got like a nice little arch
Yeah,
of
that
green?
feature, that
been some
feature in the
nice-
bottom right.
There's been some nice ctenophores and things coming through there.
Yeah.
So we can, I don't know if you want to turn the Norbit
Looking
off.
on the
or
was a
leave
bright
it
side,
on.
Andrew.
I'd say that was another krill.
Were you saying something?
some krill.
Yeah, Dan, I don't know if you want to leave the
sorry,
Norbit
Rod.
on or leave it, turn it off with the ground fault.
Oh.
or the-
If we're not using it,
Yeah, we're good. It works.
All right,
Roger.
Norbit works. Yay.
Copy. Turning Norbit off.
copy.
Norbit is off.
One thing we didn't determine is if you have to restart that topside software, or we can just turn Norbit back on and leave the software up. Would be nice to know.
Do you want to turn it? Do you want to try that now?
Sure.
Turn it back on.
Double work over here. It is on. I'm sorry.
Okay, let's see if it cycles on. Might take a bit of time.
Turn around.
Let's see. Doesn't appear that it's happy with that, but I'll leave it for a bit because it may.
Yeah,
it took a bit of time.
We did a quick test at pre-dives, and then before we moved on to getting the vehicle in the water, but it didn't come back up right away.
Yeah. I'll give it another minute. If it doesn't, then because it took a bit of time to turn on in the first
Oh,
place.
I got another question for for Dr. Freeze.
Shoot.
What is the more exciting samples that you've collected?
Oh, good question. All right, so if you ask a dozen planetary scientists that question, you'll get a dozen answers. Everyone has their favorite. So I'm going to give you my extremely biased personal opinion. There is actually two different meteorites. One fell in West Texas called Monahans. Another one called Zag. It fell in Morocco. They are the same kind of meteorite. What's really spectacularly interesting about them is that they contain little salt crystals, as in like same halite, same stuff that you get in your salt shaker. Except this particular and this is the halite in these meteorites is on the order of 4.3 billion years old. It's the oldest salt you'll ever see. It's actually turned bright blue by radiation damage from
Oh, wow.
long space. And it's even better than that, because these little tiny salt grains, which had to have been added to the meteorite not too terribly long after the formation of asteroids in the first place. We're talking very, very early in the formation of the solar system. These little salt grains actually still contain salt water. This is the oldest samples of water from the early days of the solar system. They're microscopic. The individual salt grains are on the scale of the same size as the shakers in your salt, the salt in your salt shaker on your table, or even smaller than that. When you open up the meteorite and look, they're painfully obvious, because they're these bright purple or bright blue little grains, and they're just gorgeous.
Wow.
But they are getting a lot of. They've been investigated 21 ways to Sunday, and continue to be studied. Are running the hypothesis that I'm kind of investigating with these things, and myself, and I'm not the only ones, others, is that they originally came from a body, a large asteroid that was large enough to basically off-gas water directly into space like a big comet. It would have looked like a comet. You would have seen these great. Trying to figure out the right way to describe this, because it's not like a fountain and geyser. It would look more like a comet. This is in the vacuum of space. The water doesn't come spraying off. It kind of comes subliming off. Anyway, wherever this came from, wherever the salt came from, it had to be a body large enough to have liquid salt water on it.
Wow.
And but it wouldn't have survived very long. That water wouldn't have survived very long in the original salt water that made this stuff would basically sublime off in space or freeze into ice. And so we're talking about a large asteroid, large enough to have liquid water, that then lost that water to space over time, and sprayed all this basically salt crystals into space.
I didn't know that was possible, that was something that existed. I actually pulled up a picture. I'm looking at the salt crystals online because I can, and they're cool.
Yeah, beautiful. So this is actually today on on a moon called Enceladus. There is water vapor escaping from that moon, and we flew a spacecraft through the plume of plume isn't the right word. It's not like Yellowstone or a geyser where you have like liquid water spraying up. It's more like it's evaporating off. And anyway, flew a spacecraft through there and measured it. And what's coming out of it, what's left behind as this stuff off gases from Enceladus, is mostly salt grains.
What was the first one you mentioned? There was one Zag in Morocco, and what was the other one?
Monahans.
Monahans in Texas, right?
Named after Monahans, Texas, where it fell. Yeah, fell in a clear blue sky, more or less. There was a few clouds, but came
I remember it as a clear blue sky.
One of the big Monahans meteorites actually landed in the street near a bunch of kids that were playing.
Oh, wow.
And they gathered and covered it. You can imagine their surprise.
Copy.
Roger.
Number 10.
Anyway, that one's my favorite because
Just fascinating to
you
imagine that.
Yeah.
Yeah.
And since I have no one else to contest, that's probably the most exciting.
Yeah, you have to figure that so it had to have been kept cold since it formed. It is one of the folks working on this basically did a simple test to see how much you can heat a little grain of salt and before you drive the water out of it, and it was basically room temperature. It was like 25 degrees Celsius.
Wow.
So little salt grains formed and have never been warmed since then.
Well, pretty cold out there.
Yeah. It's even weirder than that because the type of meteorite that it's sitting in could not be the source of the salt.
Oh.
Inside the salt grains themselves, along with these little pockets of salt water, there's basically a bunch of carbon. This came from there's a little more to it than that. Short version is these salt grains came from a very carbon-rich original body. And the Zag and Monahan's meteorites have very little carbon in them. They're a different type of meteorite, a H chondrite.
Oh, wow.
How do you figure that?
Well, basically the mineralogy. You know, instruments nowadays we can get into these things the size of a single salt grain and examine all the little tiny bits of material that are trapped in the halite, and it includes relatively a bunch of carbon. It contains minerals that show signs of having been wet, which makes sense. The halite has water in it, but it's a very different suite of minerals than what makes up the rest of the meteorite around it.
I suppose I didn't ask my how do you figure that very clearly. Sorry. So where might it be then that the salt originated if it was not from that meteorite?
A big part of the answer to that is that the Monahans and Zag meteorites are regolith breccias. And what that means is they are kind of compacted together material from the outermost surface of an asteroid. I mean, basically, the outermost surface gets material falling onto it. It gets impacted by, you look at any asteroid and you can see signs of craters on the surface. So you have all this cratering going on that reorders the material on the surface and makes what's called a regolith breccia. Regolith is the kind of crushed rock that it's made of. Breccia means it has a bunch of lots of different pieces, all kind of compacted together. So that's important because, all right, so the meteorites themselves came from the outer surface of wherever the H chondrites came from, and they have these little salt grains that have a mineralogy that just does not match the rest of the meteorite at all. And so the picture that it puts together is that the halite fell on the surface of this asteroid and then was kind of caught up in the compacted regolith on the surface. And later on, something else hit the H chondrite body and kicked off pieces containing the halite and sent them to Earth.
Huh.
So this is very, very well-traveled halite. It was started off on some asteroid with a lot of carbon and was shot out into space, and then was kind of swept up by this other kind of meteorite, the H chondrite body, and as the surface of that body was kind of mixed up by impact cracks. It was the halite ended up entrained in the rock, and then that was then knocked off the H chondrite body and sent to Earth. So this is my favorite because it's not only these samples of this really old water, but it's got this really convoluted story. There's no easy way to explain how you end up.
Fascinating to imagine the life and history of those salt grains.
Yeah. So that's my highly biased answer. That's my favorite.
Sounds pretty good.
It's my favorite too.
It's starting to
How's
get
it
really
going,
good.
Nimble Dredger? Nimble Excavator, excuse me.
I was just going to give it a minute or two here and see if the
Settle.
hole would clear up to
Yeah.
enough to get a glimpse of what our depth is.
Sounds
The
good.
only way I can tell at the moment is to
Stick it in there.
stick it in there and kind of see if we come up with mud or not. It makes it less than ideal because if we plug the nozzle, we're killing the venturi. So it's a venturi dredge at the moment. So without any flow, it doesn't really dredge too well.
All right.
But not sure it's going to clear. It's clearing a little bit there. But
You jinxed it.
It's also a weird angle because it looks a little bit better on the bubble.
Oh, yeah, I see what you're talking about.
Do you have a sense of how compact the material at the bottom is? I mean, is it really kind of denser and sandy, or is it muddy, or is it?
Seems it sticks to the nozzle pretty well, so it seems like clay. That kind of gray clay that we get under the sediment. Whether it has sand in it or not, it's hard to say.
That means that the meteorite could have buried itself to pretty good depth in there.
Mm.
Yeah, what do they figure the velocity was after 100 meters of water?
It would have been the same as dropping it through the water. Basically these things came. Meteorite has what we call the cosmic velocity entering the Earth's atmosphere, and that'll be on the scale of tens of kilometers per second. And then it's slowed by the Earth's atmosphere and then drops, and it will drop from 20, 30, 40 kilometers up. And from there on down, it is aerodynamically limited. It slows down all the way to the ground. And then landing in the water, it's going to basically plummet at the speed governed by the just free falling through liquid. So it's not screaming into the seafloor at tens of kilometers per second. It's going to be like dropping a bowling ball into this. Except
so if I threw a bowling ball over the side of the vessel, for example, it would bury to the approximate same distance.
Yep.
That's what you're saying.
All right.
Which we do quite often, actually, not bowling balls, but on the last job we were throwing glass bead bags.
Sometimes a
deploying
big yellow thing attached to a tether.
And they would plop into the sediment and probably, they were 26-pound glass bead bags, so they're about the size of your kitchen trash bag, half full. They would land in the sediment, I don't know, 6, 8 inches.
Yeah. It's a new sound.
Seems like the current's also going down into the hole and then picking up the dust on the way down. So.
What, any estimate on what bread loaf size of this rock would weigh?
So the measurements we've done so far seem to indicate it is a iron-rich meteorite on the order of about 6 grams per cubic centimeter. That's until we get a rock in hand. That's right.
I failed horribly at math, so 6 grams per cubic centimeter won't get me there.
6 times the weight of water.
Sorry, go ahead.
As the density, or?
Yeah. Water is 1 gram per cubic centimeter, so 6 times the weight of water.
Mm-hmm.
Yeah, so if it was a bread loaf size, so if you pick,
So
I don't know,
Yeah, pick a
half a cubic meter or something.
to pick up a gallon of water, it's going to weigh 6 times that.
So a gallon of water is what, 7 pounds, 9 pounds?
Around there.
8 pounds.
8 pounds.
So you're looking at 48 pounds in a gallon.
Yeah.
We had a
So-
gallon of this rock. Gallon-sized rock.
Round up, so 50-pound
Yep.
loaf of bread weighing 50 pounds.
So we played with different scenarios for the size of this hole, and you weren't able to constrain it very well. Anywhere between about 50 pounds and 500 pounds. Leave the 500-pound thing. I think we're closer to 50 pounds.
Well, if I hit a 50-pound bread loaf with the end of this nozzle, I'll definitely know it. So probably be able to hear it in Houston.
We can, pilot, we can go ahead and turn off the power to the still camera bottle. Like, network's just not quite clean enough to get it to turn on.
Copy.
That's a copy.
Thank you.
I'll go ahead and turn that on. It's off. Have to look at that when I get back up.
So part of the reason why I don't have a better answer for you, and I apologize, is I took all these samples and took the samples of the little pieces that we gather up out of this hole and mounted a bunch up in little polymer blocks and sanded them all down, polished them, exposed the interior, got ready for some more definitive measurements, and COVID came along and shut down all our laboratories.
Oh.
And so the samples are still sitting in my office, waiting to be analyzed, waiting for us to go back to work. But from the data I had in hand, 6-8 months ago now, it was probably an iron-rich meteorite. I was trying to get rid of the probably part when all this shut down.
Oh.
Well, it was clearing up, then we had a cave-in.
Yeah, the left side also looks like it's about to fall.
Getting down there. It's just clearing up.
Oh yeah, you can see the top a little better now.
Yeah. Can see in front of the vehicle with the brow camera though.
Mm-hmm.
If you kind of dredged into an incline on the right, it should clear up. So, because right now dust is going down and it's billowing.
Yeah, I was considering that, but time required, I don't know if it'd be.
Stick the arm in and just like, shove it all across.
All right, guys, it's just us 5 now, the core squad.
What's that?
It's just us 5 now, the core of the watch. All
Go team.
extras gone.
Yeah, let's make patches.
Who else is? That's it?
Just
That's
us.
You're
it.
back-
That's I'm
you're
I'm
back
just
there all
flying
by
solo
yourself?
back here. Yeah.
What's up with that?
All right, patch designs. Let's go.
There was
Yeah, that's your job. You've got
Oh.
an excellent eye.
There must have been 10 people in here at the
Oh yeah.
right when we went off deck. I could barely hear myself think. Surprised I only slammed the vehicle into the seabed once.
Yeah, there's a lot going on at once.
Better hurry up if you want to have a shot at using this magnet.
It's always like that on the first dive of the first cruise. It's more exciting when we have 2,600 meters of blue water. There's like
Yeah.
10 people in here, and then by
Clear
1,000 meters, there's 7.
Yeah.
By 2,000, there's
This was
down to the watch.
on the bottom at 90 meters.
They just don't appreciate the blue water.
Well, we've had some meteorite falls into deep water recently. If you're feeling adventurous, we can go after those later.
Yeah, that'd be great.
There is a really big one over the Bering Sea.
Let's go.
And another off Puerto Rico.
Oh,
The one off Puerto Rico is close enough to a radar that you can see, or weather radar, that you can see the meteorites falling into the ocean too.
oh wow. I want to see that.
So how many cosmic fragments land come into Earth's atmosphere per year-ish?
Okay. We had pretty decent handle on that, actually. If you count all of it up, it amounts to 40,000 tons of material per year.
Wow.
That's not insignificant.
So most of that is dust. Most of that is little tiny pieces. Literally dust-sized or sand grain-sized material. But enough of it that it amounts to a good 30,000 tons a year. The number of meteorite falls, larger rocks you can actually go pick up with your hand. The running estimate out there is that there is about 1 meteorite fall per day on Earth somewhere.
All
Really?
right.
Oh my, that's more than I thought. Like I would think.
Yeah. So
There should be a
that's number of
channel
fall.
dedicated to that. Channel. I'd tune
Well,
in all
we're
the
getting
day.
close. The more information that's out there on the internet, the more of these things we actually see happen. Between people's dash cams and weather radar, and,
Yeah, what are most of the
videos
ways
on
that we're able to pick up on those things?
so that goes to the second part of the how many per day. So there's a meteorite fall somewhere per day, somewhere on Earth. You figure that 70% of the Earth's surface is ocean. So there goes 70% of them. They're all in the water like this one. Of the remaining 30%, half of those are going to occur during the day. And most people, most of the time, nobody walks around looking up at the bright daylit sky. They just go unnoticed. And so now we're down to like 15% of those meteorites which occur at night and over land. And the vast majority of those are going to land somewhere that can't be recovered. It doesn't take much to hide a meteorite fall. Tall grass, swamp, or just happening far away from where anyone is, up in desert or mountain or such.
What's the
Historically,
what's the like average or minimum size to come like to ground fall for a meteorite to maintain itself before it's like just disintegrated on impact? Or is that more on density type stuff?
it's density and it's speed.
Right.
The faster something's coming in, the less likely it is to survive, and it's going. It's a non-linear relationship. Going just a little bit faster decreases the chances of survival by quite a bit. So anything coming in fast is probably not going to survive to the ground. And fast is anything over 25 kilometers per second.
Video, you want to zoom in there?
Let me see what we can. It looks very clay-ish.
You can zoom in a bit more. Thank you. Yeah, I'm listening. Okay, you can zoom out. Thank you.
Is that good?
Yes, that's good.
Vid 1. Sorry, we were switching around earlier.
To answer your question, what's the basic? Your typical meteorite fall is probably no more than a handful of little rocks, which is a big part of why they don't get picked up.
Oh.
So that's happening, daily, but a lot of them are little. This particular fall, this went into the. This particular fall into the Olympic Coast National Marine Sanctuary where we are here. This one was, estimates place it originally about a little 0.6 meters, maybe as large as a meter in size, and the surviving amount of material is. Well, we don't know. That's a little tough to answer. But one of the things that picked this event up was an infrasound network. There's infrasound sensors. Infrasound is really, really long wavelength sound. Well beyond human hearing down at the base end, and the nice thing about sound at that wavelength is that it travels extraordinarily long distances through the atmosphere. So you can have sensors that detect events hundreds, thousands of miles away, depending on the. And so this one was picked up by infrasound sensors. This kind of goes back to the earlier question of how do you detect these meteorite falls? This event was detected by infrasound. It was detected by seismometers. By that I mean the more typical. When you think seismometer, you think a device that's built to detect earthquakes. And the sonic boom created by this object coming through the atmosphere were loud enough that it showed up on seismometers.
Oh wow!
It actually showed up seismometers on land, and actually, for the first time I've ever seen, this event showed up on seismometers on the seafloor.
Quite a few of them in the neighborhood.
Oh wow!
Yeah, and it was loud. This one showed up on weather radar. Like I said, that's how we knew where to look, because it looks like a cloud falling material on radar. What else? It showed up on this one. Okay, another unique fun thing about this fall is it showed up on a weather buoy. So there's a weather buoy moored a few kilometers to the southwest of this site. And one of the things that weather buoy was measuring was the peak wave height and the direction that waves was coming from every 1 hour period. It tallied up the movement of the buoy and recorded a measure for where the waves were coming from in that 1 hour period. And you look at that data for the time of the fall, and in the 1 hour period where the meteorite fall occurred, it points toward the direction of the fireball of the meteor that produced this.
Wow.
Every every other measurement for actually several days before and afterward is all coming out of the northwest. Waves were consistently coming out of the northwest. And in that 1 hour period, it points directly back toward the fireball to the east, to the east-northeast from there. And I don't think what we're seeing in that is waves. This thing didn't hit the water hard enough to make giant waves. What it did was that sonic boom echoing out from the fireball was strong enough to show up as to basically rock the buoy back and forth and make it think that that was the biggest wave it had seen in a 1 hour period.
I like that the term fireball is the technical term. When I first heard that, I was like, oh, they're just saying fireball, but that is actually what it's called, right?
Oh yeah, there's an escalating scale of nomenclature there. You have a meteor, which is just, you look up at night, you see a little streak in the sky, that's a meteor. If it is brighter than Venus, then it's a fireball. And if it basically lights up the ground around you, it's a bolide.
What was the last one?
A bolide.
Oh.
And then you get crazy. You get into like super bolides. If you all remember the event over Russia, the Chelyabinsk meteorite fall, that was
I was just about to bring that one up.
I was going to ask you about that one. Yeah. Did you guys study that?
I did, as best as I could. We at NASA, we got a piece of that. We obtained a piece of it for research purposes and wrote up a paper describing it. The event itself was unusually powerful bolides, the most powerful one we've seen in like about 30 years.
Yeah, didn't it damage like over 7,000 buildings or something?
Yeah, it did. I've seen different numbers of the number of buildings, number of people. Various reports have put it up to or over 1,000 people were injured by basically the shock wave from this. Not by meteorites actually hitting them or striking the ground with their cosmic velocity, because they didn't. The whole thing slowed down before it fell. But it made a powerful enough blast that it shattered windows all around the fall area, and people were hurt by flying glass.
Yeah.
This one here sorry, go ahead.
I was just going to say, I listened to a podcast on it recently, and they said, I don't know exactly if this is true, you can confirm that they didn't see it coming. Is that true?
Yeah. Yep. And the reason being is because, short version, it came out of the direction of the sun. You can't point telescopes into the sun and expect to have a working telescope for very long. So no one was looking in that direction, the short version. What else can I tell you about this? Oh, sensors. So there's actually a very exciting new way for watching meteorite falls that has only been available to us for us being the world, because this is publicly available data. It's only been available for about a year now, and that's the geostationary lightning mapper.
Nice.
Oh, that's the thing that I lost it. I had it. It's gone.
So that's a satellite?
Yeah.
Oh, it's a NOAA satellite. So here we are in the Olympic Coast National Marine Sanctuary, which is administered by NOAA, and observed this meteorite fall on the NEXRAD nationwide weather radar network, which is administered by NOAA, and the latest weather satellites, GOES 16 and 17, which have this lightning mapper, are administered by NOAA. So NOAA didn't mean to, but they've become like one of the best sources of finding meteorite falls out there.
They're becoming too powerful.
They got into the biz.
I was going to ask you actually if that sensor was on GO 16, because that, I mean, when that went up, I saw the